Hello, I've been away teaching and I'm feeling a bit rusty, but I'm back to talk about 3-atom electrocyclizations. Today's focus is predominantly going to be this reaction shown here, where we have a 3-atom pi system with either a positive or a negative charge undergoing cyclization to give a cyclopropane species. So given we're looking at a 3-atom species, we can look at the orbital configuration of the pi orbitals as we start to add electrons into them. And for a cationic propane species, we're dealing with 2 electrons, which populates this psi1 lowest energy configuration of pi orbitals. The reaction is shown over here on the left, specifically entailing 1, 2, 3 carbon atoms. There is a delocalized double bond across those 3 atoms, as well as the positive charge. This can cyclize going in this direction, or it can ring open going in this direction. So how does this electrocyclization occur? We're going to focus on the cyclopropane form and how it ring opens, even though it can proceed in a forwards or a backwards manner. So looking at the central structure, we can see this bond is the one that needs to break in order to form the ring open species, and the combined orbitals of the homoform making up that bond are shown. Now, to break this bond, we need to essentially rotate the 2 p orbitals donating electron density into this bond. And we could rotate those p orbitals either in a disrotatory manner, meaning that one of the p orbitals rotates clockwise and the other p orbital rotates in a counterclockwise direction. And depending on which way you go, the R groups could arrive at this conformation shown here. If you spin those p orbitals in a disrotatory fashion in the opposite directions, you would wind up with the R groups here and here instead. So that's one option. The other option is that you could rotate these 2 p orbitals in a conrotatory manner, meaning that you rotate them both in the same direction, so both clockwise or both counterclockwise. And if you do that, you'll arrive with a structure that might look like this, with the R groups on the outermost position, or if you rotated them in the other direction, they may wind up in the innermost direction. Just to try to give you a better picture of how this would look, if we look at this structure shown here, I've included the imaginary direction whereby we are looking at this molecule, and we're gazing at these overlapping p orbitals, shown in green, that makes up the carbon-carbon bond. Here are the 2 options shown down here. There is this disrotatory mechanism whereby we break apart this bonding interaction by twisting these 2 carbons so that the p orbitals peel apart in different directions. So the left-hand p orbital is rotating in a counterclockwise fashion, the right-hand p orbital is rotating in a clockwise fashion, and you can also see the effect that this has on the R groups. They are rotating in the same direction as the p orbitals do when that bond breaks. Looking now at the conrotatory example, we can see that both p orbitals are now rotating in a clockwise fashion, and indeed the R groups are also rotating in a clockwise fashion. Both are valid options for breaking that bond under the right conditions to affect that form of rotation. And those right conditions are spelled out in the Woodward-Hoffmann rules, whereby depending on if you're using heat or photochemistry to affect your reaction, and the number of electrons that make up your pi system, only one option, conrotatory or disrotatory, is going to be favoured. Now we're dealing with a cationic 3-electron pi system, so 1, 2, 3 pi orbitals minus 1 to account for the positive charge. That means 2 electrons total. So we're dealing with a 4n plus 2 categorization whereby the n is equal to 0. All the reactions we're talking about today are thermal processes, so we're dealing with this column shown here, also known as the ground state column. So all of these transformations involving this chemical species should be disrotatory. So we're in the ground state and we're doing our reaction thermally, which means it's going to occur by a disrotatory mechanism. However, there's still 2 possibilities for disrotation. We can choose to either twist the R groups inwards or outwards to affect the transformation. Here is our chemical species. We've got our cyclopropane. X is a leaving group. The bond we are going to break is situated between these R groups, and the 2 options for disrotation are shown. Focusing on the left-hand side, we could rotate the R groups inwards. So looking down here at the transition state, left-hand p orbital, we're going to rotate it clockwise. Right-hand p orbital, we're going to rotate it counterclockwise. This is going to bend these R groups towards one another. And ultimately, when the bond breaks, we'll arrive at this product shown here, with these R groups in a cis arrangement in relation to one another. Our second outward option, transition state, is shown down here. P orbital on the left, we're going to rotate that in a counterclockwise direction. P orbital on the right, we're going to rotate that in a clockwise direction. In so doing, our R groups are going to rotate outwards, giving us this product shown here, whereby the R groups are sort of in a trans configuration in relation to one another. So based on looking at those two disrotatory possibilities, we can conclude that the disrotation whereby the R groups form a product where they are situated outwards or trans in relation to each other is going to be sterically favoured. So if there are no other considerations, this is the product that is going to be favoured at the end of the reaction. However, let's imagine a situation whereby these R groups are linked to one another. In that situation, there is no way whereby you can stretch them outwards because they are held together by this bonding interaction. For this species to undergo a disrotatory ring opening, these R groups must rotate inwards. The strain of them moving outwards would be too much for that reaction to proceed. To briefly focus on the leaving group and its influence on the reaction, it's worth noting that the ring opening occurs simultaneously to loss of the leaving group, and that the leaving group directs the stereochemistry of the product. So here we have two related chemical species. The only difference between them is the location and orientation of the tosyl leaving group. The bond that we're going to break is in exactly the same place. The steric constraints around the R groups are the same, yet we see that there are two different products, and the rate of one of these products is considerably faster than the other. Let's have a look at why that is. So to do so, we need to draw out the orbitals for the lowest unoccupied molecular orbital of the leaving group. So essentially, this is the electron configuration as this bond is breaking, releasing the leaving group. And we can see this big lobe of electron density positioned on the opposite side to where the leaving group is situated. Because we've got this big cloud of electron density here, this actually stabilizes disrotation of these two p orbitals as they bend upwards, like so, giving us this stabilization force shown here. As these p groups are rotating upwards to interact with this electron density, the R groups are moving outwards into finally this arrangement shown here and giving us this big enhancement in the rate. Conversely, let's look at the other situation whereby the tosyl leaving group is situated above the cyclopropane in the same location adjacent to the methyl groups. Looking at the LUMO orbitals, we can see that the electron density is now situated below the cyclopropane ring. And these two pi orbitals are going to disrotate downwards to interact with that electron density, but also creating this steric clash above the cyclopropane ring. So for this reason, the leaving group is going to direct the disrotation direction, resulting in ring opening. So we can summarize this by saying that R groups that are cis to the leaving group, so that would be this situation down here, these R groups are going to rotate inwards, giving us this product here. And this creates a steric issue, so it's not going to be very fast. Conversely, R groups that are trans to the leaving group, so shown here, this situation, these R groups are going to rotate outwards. And in so doing, they are not going to be held up by the same steric issues as the cis situation, so we get this much faster reaction here, forming this product shown at the top. The same holds true if the R groups are tethered together into a cyclic system. Now when the leaving group is trans to the tethered R groups, it wants to open up by rotating these pi orbitals outwards, and it creates this sort of nonsensical structure I've drawn here. and this has a serious strain issue. So the rate is going to be very slow if the reaction proceeds at all. However, in a cis situation shown down here, leaving group is cis to the R groups, which are tethered together. Now the leaving group is benefiting this inward rotation, and we can see that the rate of forming this product is like in the order of 1,000,000 times faster, just through proper positioning of where the leaving group is in the starting material. Let's now look at a named reaction that makes use of this electrocyclization chemistry, and that would be the Favorsky rearrangement. The reaction is shown here. We have a cyclic ketone, you apply hydroxide and heat, and you get this rearrangement to form a carboxylic acid with contraction of the ring from a 6-membered ring to a 5-membered ring. Looking now at how this proceeds, first thing to occur once we add the hydroxide is we get ketoenol tautomerism. With the application of heat, we lose our leaving group, which is chloride in this instance, and that creates this ylide type species here. But we can see we've got this 1, 2, 3 cationic propane species, exactly the kind of species we've been talking about. These are the R groups here. We can see that they are tethered together. We know that it needs to be a disrotatory mechanism going between the cyclized and the open form, which allows us to predict what this cyclized species would be. It's drawn over here along with the disrotatory ring opening mechanism to transfer between these two forms. We can take this cyclized species, draw it down here, and this allows us to understand why there is this ring contraction and how we wind up with a carboxylic acid product. So taking this fused form and our hydroxide, we can attack the base of the ketone with ring opening to give us our 5-membered ring carboxylic acid product. And if we work this up with some acid, we're going to arrive at our final product shown here. So if all that was talking about 3-atom species with 2 electrons, so the cationic cyclopropanes, what about 3-atom species but 4 electrons, anionic cyclopropanes? Well, if we look at the difference over here, we can see that with our 2 additional electrons, we are now in this Psi2 non-bonding region, and we know that the cyclization occurs between these terminal carbons, and the arrangement of these p orbitals is now flipped. So previously these had the same orientation, our p orbitals, now we have opposing orientation. How a typical reaction might look is shown over here. We've got our 1, 2, 3 carbons with a double bond shared across them, and we also have this anionic charge delocalized over these 3 atoms. And this can undergo cyclization to give us this type of cyclic species shown below. Key difference to before, we've got this additional lone pair of 2 electrons present in the products. Now, if all of our 3-atom species with 2 electrons was a disrotatory ring closure mechanism, because we've got those 2 additional electrons now, the means of ring closure has now become a conrotatory mechanism. So I've drawn in the line of sights shown here. If we take this p orbital and we rotate it in a clockwise fashion, this lobe is going to rotate inwards. Similarly, looking in this direction at this p orbital, if we rotate this in a clockwise mechanism, this lobe is going to rotate to meet this one, allowing us to form this bonding combined orbital here. Just to show I'm not making this up, we can look at the Woodward-Hoffmann rules one more time. We're dealing with 4 electrons now, so we're dealing with the 4n pi electron rule. We're still dealing with ground state thermal processes, so we can see that conrotatory is now the allowed means of ring cyclization. I'm not going to go through the whole thing all over again with 4 electrons, so I'm just going to show you an example of 3-atom species with 4 electrons, specifically these azopropane cycles and how they ring open. We can see it's going to be a conrotatory mechanism. There are 2 options once more. You can either rotate both p orbitals in a clockwise fashion, or you could rotate both p orbitals in a counterclockwise fashion. If you have two bulky R groups and you try to rotate them both inwards, there will be a steric clash, which means that rotating them outwards is more sterically favoured. However, if those two R groups are linked together into a cyclic form, the only way it can proceed is to rotate them inwards, as the strain of trying to pull the ring apart is going to make outward rotation disfavoured. So to sum up, 3-atom electrocyclizations, they're an interesting explanation of certain cyclizations that can proceed while seemingly ignoring Baldwin's rules. These reactions follow on nicely from other pericyclic rearrangements and cycloadditions, mainly because they use the same frontier molecular orbital theory that we've already learned about. Bear in mind that all of today's samples all correspond to the 3-atom thermal processes only. I will talk about greater number of atoms in a subsequent video, but if you're looking at light-driven processes, disrotatory and conrotatory are going to swap around, so bear that in mind. But that's all for today. Thank you for watching.